Are you guys ready for our last electrochemistry video? Woo! Power to the people! Video number 15, technically video 11 if you take out the review videos. We're going to look at electrolytic cells. Remember, electrochemical cells is the big umbrella of everything. Well, under electrochemical cells, you can have cells that are spontaneous, right? Spontaneous reactions with E cell greater than 0. And you can have non-spontaneous ones with E cell less than 0, so they're negative, which don't run. Well, the ones that are spontaneous are called galvanic or voltaic cells. That's all we've been looking at, because why would you do it otherwise? You can't get any useful work from it, no electron flow if it's not spontaneous, right? But we can take a non-spontaneous reaction and force it to happen if we take some kind of energy from outside. Maybe we could take an external battery, drive electricity into it, or plug it into a wall or something at home, like recharging a rechargeable battery. Plug it in the wall, electricity flows in. Now we've got external work coming in. That can force a non-spontaneous reaction to occur. That's called an electrolytic type of electrochemical cell. So we're driving a non-spontaneous redox reaction to occur by forcing electricity into it. So this is the opposite of a galvanic or voltaic cell. What's weird is the anode and the cathode switch, right? Because in this case, the electrons are flowing in the opposite direction. Instead of flowing from left to right, they're going to flow right to left. And the cathode and anode, the electrons change signs. Because originally in a normal galvanic cell, the anode is where oxidation occurs. So electrons are being produced there. So that's negative. And they travel over to the cathode, right? And the cathode is positive in that case. But that flips when you have an electrolytic cell, because in an electrolytic cell, you take a battery and drive electrons away from the anode, right? They're withdrawn from it, and then the cathode becomes negative due to that. So everything's just backwards. It's really weird. It almost hurts my brain because we've been doing it one way for so long. So normally in a galvanic cell, the anode's here, which is negative, and the cathode's here, which is positive. But now it switches in electrolytic cell. This becomes the anode, woo, and this becomes the cathode. So electrons are going right to left rather than left to right. Oh, my head hurts, right? And because where the battery is sucking electrons away from the anode, it becomes positive, and cramming them into the cathode, that becomes negative. So all the signs are switched and everything. I'm so confused. Where's the ambulance? Dial 1-800-WHAM-MOMMY. WAHMOMY. Let's draw a picture of it. Here is a picture of what I was attempting to say. All right, sometimes pictures are way easier. So we've got an electrolytic cell setup. Now, imagine if this was a galvanic cell where we have the zinc. Normally we have the zinc anode and the copper cathode. Electrons are produced here. Oxidation occurs. They go over here. Reduction occurs. Nitrates go this way. Potassiums go that way. And we have a positive E cell on a voltmeter. All right. But now let's switch it around. Let's say it's the other way. We're going to have it go the other direction. We're going to oxidize the copper and reduce the zinc, which is the backwards reaction, which has a negative E cell. Same value, but a negative E cell. So it's not going to happen on its own. We need a battery or some kind of external electricity flow to go through there. So what we're going to do, if we set up this battery and hook up the terminals, if this is positive, it's going to suck electrons away from the copper, right? Which used to be the cathode, but now it's the anode, and it used to be negative, and now it's positive. So we're draining electrons away from the anode. That's why it's becoming positive. And oxidations occur. So what happens is, as the electrons get sucked away, copper atoms are forced into solution as copper plus 2 ions. Right? So it's forcing the oxidation. It doesn't want to happen on its own. Right? It needs an external power source. All right? Well, those electrons come through and are forced and crammed into the zinc, which is now the cathode. Used to be the anode, now it's the cathode. Because we're cramming electrons onto it, it becomes negative. So zinc ions from solutions bonk into it, boop, pick up electrons, and plate out. So the zinc becomes reduced at the cathode. So the cathode anode switch sides. It's kind of funny. And they switch signs, not only sides, but signs. And the ions flow the opposite directions what we're used to in the salt bridge, right? Remember, anions flow towards the anode as every copper 2 ion produces in solution. 2 nitrates come over to keep electrostatic balance. And for every zinc ion we lose over here, 2 potassiums fall in. The cations go towards the cathode to maintain electrical balance. So from a distance it looks the same as a galvanic cell, but when you really get your little magnifying glass and go, ooh, the signs are switched on the cathode anion, they switch sides and the ions are flowing the wrong way and the electrons are flowing the opposite direction. What can we do for this? There's several different things the textbooks talk about. I'm going to skip a lot of it though. I'm not going to go through batteries. You can read through the sections on batteries, which are a lot of fun, but we just typically don't have time in a regular crammed semester, right? We just don't have time. So I'm going to focus on quantitative electrolysis, where we're going to cram electrons into a non-spontaneous reaction and do what's called electroplating, which is a lot of fun. I did this as one of my voluntary labs my senior year, where I took a pen. I wanted to measure the copper content in pennies pre-1982 and post-1982. So I did the experiment twice, and I dissolved them up in some acid and got the copper ions in solution. Then I took this wire mesh, this dry wire mesh, and I weighed it. And then I hung it in and hooked up an electrolytic cell and ran some electricity through, and then I plated the copper. So I took the copper 2 out of solution and plated it as solid copper onto the wire mesh. I don't know if that was platinum or not. Can't remember. That was a long time ago, man, like over 3 decades ago. I just turned 51 on Saturday. Yay! We're moving along, baby. So what I did is I weighed that metal mesh before the reaction, and then after I sent the electricity and plated all the copper out, and then I weighed it again, dried it off and weighed it again. So I could measure the mass of copper I pulled out of solution and solidified, and then I could compare that to the mass of the penny I weighed before, or cent technically, and I could get the percent. So before 1982, it was around 95% copper. After 1982, it was close to 5%. I forget the exact values, but it was a fun experiment to do. Set it up. It was an optional one. We had to design our own experiments our senior year for one time, and that was the experiment I designed because I'm a coin collector. It's a lot of fun, so I was curious that pre-post 1982, and then I checked my values versus government references for what they say are the percent compositions in the cents before and after 1982, and it was spot on. It was pretty cool. And that's all I did. I set up something similar to that. You also see electrolysis of water, which is one long time ago when they first realized water wasn't an element. Oh, we had that wrong for centuries and centuries. So they put electricity into water, and the water reduced at the cathode and oxidized at the anode. And you could produce hydrogen gas. You could see the bubbles at the cathode and oxygen gas. You can see those at the anode, and you can see you collected, twice the volume of one from the other. It was a really simple, neat experiment, but they were able to realize water is not an element, right? It's a compound. They did that through electrolysis of water. Neat. So I'm going to write up a couple things we have to watch out for, over potentials and side reactions. Not going to focus too much for my particular class for that, but I'll write them up real quick. Couple things to watch out for, and again, I just want to bring them to your attention because the real world can get weird sometimes. It's always harder than you think, unfortunately. So in this class, we're not going to worry about these two things. I just want you to be aware of them. So let's say we're hooking up, we're sending a voltage in to drive a non-spontaneous reaction to occur in an electrolytic cell, and we could actually measure what the voltage required would be, right? Do the 2 half reactions, add them together, and it'll be some negative value. Say it's negative, 0.521 volts, right? So if you put in 5.521 volts from an external power supply, boom, it should run, but not always. You're like, no, why is it not running? Sometimes you need more voltage than you thought because of something called an overpotential. Weird stuff, not going to get into the details, can happen at electrode surfaces, especially like if we're producing gases. Those little bubbles can get in the way. So sometimes it just requires a little more oomph than you would have possibly imagined. Again, I'm not going to go into details on that, but it can happen. You can read about it if you're really interested. Yep, sometimes it's worse than you think. Another thing that can happen is a competing reaction, right? Because you don't just have, like, for example, a solution of iron 2 ions. you have to have an anion in there, like nitrate ion or chloride ion or something like that. Well, every once in a while, you're driving some electricity through there, and you're expecting the iron to reduce, and it doesn't. The anion does, or the other species reacts, and you're like, darn it, that's not what I expected. You got to be careful with that sometimes, especially if you're in aqueous solution. Right, you got water, so you got the cation that's hydrated in water and the anion that's hydrated in water. You're expecting, right, maybe the cation to reduce to the metal or something like that, but well, gosh darn, you never know. Sometimes that water might reduce to hydrogen gas instead, and you see a bunch of bubbles. You're like, I'm not supposed to get bubbles here. What's going on? And that is just more likely to happen than what you would expected. Or sometimes water can get oxidized to O2 gas, right? So you take that. So in this case, you're taking the +1 hydrogen going to 0. Right? So that's being reduced. In oxidation, you're taking the -2 oxidation number in water and going to a 0 for O2 gas. That can happen, side reactions. Don't worry about it in this class. Think about it, read the stuff in the textbook, but on my exams, don't worry about competing reactions. This is tough enough, right? I just wanted you to be aware of something that happens in the real world sometimes. Or if you're in lab, you're like, boom, I wasn't expecting bubbles there. What happened? So what I do want to focus details on is quantitative electrolysis, right? Electrolysis is when you're adding electricity to an electrolytic cell to make a non-spontaneous reaction proceed. And what I talk about is electroplating. It's a lot of fun, right? You can cover things in like silver plating or chrome plating. It's kind of cool. We can actually do some dimensional analysis and combine that stoichiometry and dimensional analysis with electrochemistry, and we could calculate the mass of metals, like I did in my lab, that are produced by driving electricity into a cell like this. And like I said, when I measured the amount of copper that I plated out, it was a whole lot of fun. So let me show you how to do that. It's quite straightforward, nothing particularly new. Just have to introduce one new concept called amps. Not the drinking energy drink amp. Amperes. You ready for current? Here we go. So here is our new term for the day. We're going to do quantitative electrolysis, one of my favorite things. We're going to use electricity to force a non-spontaneous reaction to occur. So we could take a metal ion in solution, a cation solution, cram electricity into it, and force it to become the neutral metal. And we can make that played out on something called electroplating. Tons and tons of fun, right? You can dip something in a solution, run a current through there, pull it out, and it's all plated in. Right? Again, just that metal reducing and plating out as the solid neutral atoms on top of some kind of surface, right? So the amount of electric charge we're using, right? We're flowing electrons into it. How do we quantitatively measure the amount of electric charge that we used? Well, that is measured using this term called current, and that has that symbol capital I, with units of amperes, and I know you've all heard of that. Capital A are just amps for short. All right, so amps is the current, the electron flow, the amount of electric charge flowing per unit time. So be careful with that. That's what's going to hurt you, man. When you grab an electrified wire, it's the current you're worried about. Been there many times, right? So an ampere is the amount of electric charge that has flown over a particular unit of time. Typically, we do that per second, how much electric charge is going per second. And so that would be, so an amp, an A would be a coulomb per second. We can use that as a conversion factor. So if we have the amount of time we're running the electricity through, and we know the current, we could determine, right, if we know the current and the time, we can calculate the amount of electric charge. And since we know Faraday's constant, 96,485 coulombs per mole of electrons, we can use this to calculate the mass of a solid that will be produced. Let me show you the dimensional analysis process for it, but it's pretty straightforward. So kind of fun. I like this section because it introduces amps. Amps are fun. Here's your thinking process, your game plan. And you can, this is one of those types of problems that goes back to first semester general chemistry, where you can kind of figure out how to do it without really knowing what you're doing, just by following the unit line equations. Incredibly powerful way, dimensional analysis, of solving problems. But if we're going to do a quantitative electrolysis problem, we're going to plate a metal, we're going to reduce it so it comes out of solution and plates out. And we want to calculate the mass that comes out. Here we go. How much is plated out of solution? Start with your time. So maybe you run a current through, provided, let's say we're provided a current, some kind of amps, so 2.2 amps or something, and a time. So say 15 seconds or 2.5 minutes or 3.7 hours, whatever it is. 87, light year. I don't know, some kind of weird time unit. Light year's not really a time unit. We're going to start with the time, whatever the time is. And again, that could be in seconds, could be in minutes, could be in hours. Anything else is kind of weird. Let's figure out how much electric charge was put into that solution during that time frame. So we need the current for that. So you'll be provided the current, a certain number of amps. And remember, an amp is a coulomb per second. So we can use coulombs per second to go from seconds, or if you're in minutes, say go from minutes to seconds or hours to seconds. Get to seconds, whatever you got to do. Then use the current to convert seconds to coulombs, right? Using the definition of what an amp is from the current. Once you have the amount of electric charge, we can get that to moles of electrons using Faraday's constant, 96,485 coulombs per mole. That'll give us moles of electrons. Then you look at the half reaction, the reduction half reaction, and you can convert from moles of electrons to moles of that particular metal. It might be a 1-to-1 mole ratio, 2-to-1 mole ratio, 3-to-1. It just depends on what the charge. If it's aluminum plus 3, that'll be a 3-to-1 ratio, 3 moles of electrons to 1 mole of aluminum. If it's silver plus 1, it'd be a 1-to-1 mole ratio. If it's copper plus 2, it'd be a 2-to-1 ratio. Right? Pretty easy to tell from the half reaction. Once you have the moles of metal, just use the atomic mass, right, to figure out how many grams you got, or milligrams or nanograms or whatever weird units your professor wants you to convert them to. Let's do an example, show you how easy these are. Expect this kind of problem on quizzes and exams. They're usually pretty quick ones. Only takes you a minute or two to do if you know what you're doing, if you've done all your practice, right? What mass of gold, like gold, silver and gold, yay, are plated out by running a current of 1.23 amps for 12 minutes. All right, for 12 minutes. Should probably specify what the gold's starting at, because gold can be several different charges. So let's say this is like a gold 3 solution. So let's do that. Let me add that. Because how do you know what the starting charge is for 12 minutes? Let's add this. Let's do a gold 3 nitrate solution. There we go. So now you know gold's going from a +3 to a 0. We're going to be plating that out, so that'll be 3 moles of electrons. We can do that half reaction. Don't worry about side reactions. Don't be concerned with the nitrate ion reacting rather than the gold. So let's set up our half. I like to set up my half reaction first. So this is my reduction half reaction. We don't need the electrode potential. That's not necessary for these problems. So we've got the gold with a +3, right? That's going to pick up 3 electrons to form solid gold. The solid gold densest. Right? Do you see the 3-to-1 mole ratio there? That's something we're going to need in our process. So see if you can do this on your own. Start with the time. Right? So let's go minutes to seconds. Convert the minutes to seconds. Then use the current, which is amps is coulombs per second. We can get to coulombs. What's the total amount of electric charge that we jammed into there? Once we have the coulombs, you can get to moles of electrons using Faraday's constant, right? So start with minutes. Go to seconds, go to coulombs, go to moles of electrons, just like you would for any kind of dimensional analysis journey. Once we have moles of electrons, actually we want to go to the solid, right? Let's go to moles of gold. And then once we have moles of gold, we can go to grams. Now, it didn't specify the units of the mass. So you can do any units you want. Just leave it in grams, but if it had asked for pounds or, centigrams or something, or kilograms, then you could do one more conversion using metric conversions or whatever's necessary. So this is a 1, 2, 3, 4, 5-step process. Give it a shot. Show me how the units cancel out. You should end up, everything should be canceled out except for grams of gold on the upper right-hand side. Make sure you've got your trusty periodic table. You're going to need that for your gold. Ow! All right. So you need that molar mass of gold right there, 196.96655 grams per mole. And depending who your professor is, they may truncate that to 2 decimals or whatever. I just like to use whatever on my periodic table. Have at it. Let's see what you get. Why should I pause it? Let's just go do it. I was about to pause it. So we have 12 minutes, all right? And every minute, right? Hopefully you know how many seconds are in a minute, correct? So we've got 60 seconds per minute. Now let's use our amps. Now remember, amp is a coulomb per second, right? We don't need to show that. So let's just write it. So we have 1.23 coulombs per second. So minutes cancel out, seconds cancel out. That's the whole reason we're using that current there. So we can get the amount of electric charge. Now we can use Faraday's constant to convert the coulombs into moles of electrons. And I will always provide you Faraday's constant. So 96,485 coulombs per mole of electrons. That allows us to cancel out coulombs. Bye-bye, coulombs. Now we can do the 3-to-1 mole ratio. So there's 3 moles of electrons needed to produce 1 mole of solid gold. We can cancel out moles of electrons there. And last step, let's take that molar mass of gold that I showed you on my trusty dusty periodic table. That's a lot of things. I don't even know if I can read that without my glasses here. So for every mole of gold, oh my goodness, I got to hold this for. Just wait, 196. I really should get my glasses. 96655 grams of gold. Oh, I love dimensional analysis. Unit line equations just rock. They rock. So simple to do if you know what you're doing. What's the only unit left? Grams of gold in the numerator, my friends. This is all multiplication division, so we're limited by significant digits. Let's erase that. So we've got, so it doesn't say if that 12 minutes was exact or not. It's a time measurement, so I'm assuming it's not. I would go 2 significant digits on the 12 minutes. The 60 seconds per minute is exact. The current is not, but that's 3 significant digits. Faraday's constant won't matter because it's 5. The 3-to-1 ratio is exact from the stoichiometry. And our atomic mass has a lot more significant digits than we need. So I think we're limited to 2. Get out your trusty calculator. And to 2 significant digits, I get 0.6026 grams of solid gold. Double check me. That is closer to 0.60 than 6.1. So when we round it, we go 0.60 grams of solid gold plated out. That's the same way it's going to be every time. The only difference would be the time, the current, and the ratio here from the reduction half reaction. Now I could flip this problem around backwards and say, hey, to get a mass of 0.60 grams of gold, how long do I need to run it at 1.23 amps current? So you have to solve for the time. You should work it backwards. Or I could say, hey, if I run something for 12 minutes to get 0.60 grams of gold, what current would I need? And you just solve for the current. Right? So yeah, you can work it forwards and backwards, but this is a lot of fun to do. That's it for our electrochemistry journey, my friends. We're done. We are almost done with this entire class. Just a little bit more. We're going to do some titration curves, and that's the end of it. Yes!